Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching. Your Notre Dame live stream will begin soon. Thanks for watching.
And welcome to the George B. Craig Jr. Memorial Lecture, which we do every 2 years. I think many of you here know Dr. Craig, either personally or you know his legacy. Dr. Craig was recruited by Father Hesburgh to come to Notre Dame in 1957 after getting his undergraduate degrees at Indiana University and his master's and PhD at University of Illinois. And that's when Father Hesburgh wanted Notre Dame to become a research university. And somehow he convinced Dr. Craig to come at a time when there really was no research program in vector biology. But over the subsequent almost 40 years or so of Dr. Craig's career at Notre Dame, he built up a world-renowned vector biology program. And as I've said to many people, I don't think in my career in global health I ever worked with an entomologist or vector biologist who hadn't done undergrad, grad school, or postdoc at Notre Dame. And so in 1983, Dr. Craig was actually the first Notre Dame faculty to be elected to the National Academy of Sciences. And Professor Nora Bazansky, who's a vector biologist, who's the second and most recent faculty to be elected to the National Academy of Sciences, says that anyone in vector biology can trace their roots back to Notre Dame because of George Craig. When assessing the importance of vector biology at Notre Dame, Nora says, that's like asking, well, why is football important to Notre Dame? So that's a legacy of Dr. Craig. Again, during his time here, I think he had 40 doctoral students, 38 postdocs, over 500 articles, and again, was world renowned for his expertise and frankly put Notre Dame on the map in so many ways that we still benefit from. And one of the people, so first of all, I should say that we're very lucky to welcome back to campus Sarah and her husband Bill, Sarah Craig, George's daughter. Sarah spent her career here at St. Mary's of Notre Dame, and we're always happy to have her back, not just every 2 years, whenever you want to come back. But, and one of the people who can trace his roots in entomology, vector biology, to Notre Dame is our speaker today, John Gimnig. John did his undergraduate degree, a Bachelor of Science in Biological Sciences, class in 1991, before he headed off to UC Davis, where he did his master's in epidemiology and a PhD in entomology. So the epi-ento. And I first met John when his career was kind of knee-high to a grasshopper when he first came out to Western Kenya, where he was CDC, where he provided some key entomologic support to a huge randomized controlled trial of insecticide-treated bed nets. And John has been with CDC now for over 20 years, where he's head of the operations research part of the division of entomology, in the entomology branch of the division of Parasitic Diseases and Malaria. John, again, is world renowned on so many different levels, not only at CDC, but provides key support to the big programs that we were familiar with, the President's Malaria Initiative, and sat on tons of different WHO committees and continues to do that. And I should also say that John has ongoing collaborations with several faculty in the Department of Biological Sciences and Research. So join me in welcoming John.
So thanks for the introduction, Bernard, and thanks to the Tech Institute for inviting me here. It is an honor to be giving this Craig Memorial Lecture. I actually can trace my roots directly back to Dr. Craig. In fact, he had a significant impact on my career. I had actually no thought of becoming an entomologist, and I met him at Undert, and he convinced me to take his medical entomology course, and for me, some years later, here I am. So as Bernard mentioned, I started my career in malaria in Western Kenya as part of this large-scale trial of insecticide-treated nets. I've continued to conduct research in Western Kenya since that time, so over 20 years, and I thought I would try and focus most of this lecture on what's been happening in Western Kenya, but I wanted to have more of a global perspective. And as I was putting things together, I also kind of wanted to put in a bit of a historical perspective, largely because if you look at what's happened in malaria control in Africa, much of it is very recent. Africa, despite being the continent that bears the heaviest burden of malaria, was largely ignored for many, many years. I'm going to start with going back to our earliest beginnings of our scientific understanding of malaria. The parasite was first identified by Laveran in 1880. And even at that time, the idea that insects could transmit pathogens of disease was kind of a fringe idea. It wasn't until people like Patrick Manson, who showed that lymphatic filariasis, the parasites could be taken up by mosquitoes and developed in mosquitoes, that this theory started to gain traction. He had an influence on Ronald Ross, who is credited with actually identifying or demonstrating that malaria could be transmitted by mosquitoes. Ronald Ross actually worked with Aedes aegypti and bird malaria, and it was Grassi that eventually showed that human malaria could be transmitted by mosquitoes. So this actually opened up a lot of avenues for malaria control. Up until then, the primary way we had to deal with malaria was treatment with quinine, which is not a pleasant drug to take. So I'll start in the U.S. just because we have a lot more documentation of what happened here. In 1914, the Public Health Service started, and one of the things that they were involved in was larviciding to kill the mosquitoes, and that was focused mostly on using oils and Paris greens, things that we really can't use anymore. They also did some education campaigns. You can see on the left, they encourage people to screen their houses, and that's something that's I'll talk about a bit later. And then during the Depression era, a lot of the programs that were instituted actually took the idea of malaria prevention and control into account. So the Tennessee Valley Authority actually used water management practices to reduce mosquito breeding. And then the Works Progress Administration actually hired people to dig trenches and drain swamps, and you can see that down here on the lower right. A lot of that shifted during World War II when the focus became on protecting troops. And by this time, malaria was really down in the South. A lot of our bases were down in the South, so there was big emphasis on, first of all, keeping the troops free of malaria before they were sent off overseas, but then also protecting the local population from troops that might have come back with malaria. After World War II, the malaria control in war areas morphed into the Communicable Disease Center, which eventually became the CDC of today. And their primary goal at the start was to eliminate malaria from the United States. And they did that largely through house spraying with DDT. So this slide shows just some of the decline of malaria. You can see that back in the 1880s, it was widespread in the United States. By 1912, it had receded until it was primarily in the southern U.S. And then on the right, we show the decline as it relates to the Tennessee Valley Authority, the Works Program Administration. And then eventually at the very end, you can see that DDT came in right around here, and there was a pretty rapid decline in malaria cases in the United States. So talk a little bit about DDT. These days it's a controversial topic. There's a strong attempt to phase it out, but when it was first discovered, actually, well, it was first discovered in 1874, but it was not until 1939 that it was realized that it had these insecticidal properties. And there was a lot of excitement about that because not only did it kill insects, it was very cheap, and it had low toxicity to humans, and it had a long residual life. And soon after its discovery, it was actually implemented for house spraying in the United States. As I mentioned, and then by 1949, malaria was considered, the United States was considered free of malaria as a significant public health problem. And by 1951, CDC had actually shifted their activities from implementation to primarily surveillance. So that generated a great deal of optimism that we could replicate this in other areas. One other event that generated a great deal of optimism was the elimination of Anopheles gambiae from Brazil. So Anopheles gambiae is a very efficient malaria vector, but it's endemic to the African continent. Well, in 1930, it was actually discovered in Brazil, in the northeast, just outside the port of Natal. They didn't do very much about it early on, and it gradually spread to cover an area of about 54,000 square kilometers. And for reference, that's about the size of the state of West Virginia. And then in the late 1930s, there were several large epidemics of malaria, several 100,000 cases and thousands of deaths. I found one writer who actually suggested that they were going to have to abandon this area because the malaria was going to be such a problem. Well, they brought in this man, Fred Soper, who's who's very well known for his efforts to control mosquitoes. He'd also worked on eliminating Aedes aegypti from a number of countries in the Americas. And he began a program based entirely on larviciding, again, using Paris green. He was really almost like a military commander. He ran a very tight ship, and he tracked where his spray operators were, and instituted a very aggressive supervisory program. And they actually managed to eliminate eliminate this mosquito from northern Brazil in just under 2 years. They actually did it ahead of schedule and under budget. And they returned, like, I think about 20% of their funds back to the Rockefeller Foundation. So that, again, created a great deal of optimism that we could control malaria, or actually even eliminate malaria in much of the world. The next step that occurred was the Sardinia project. And I saw this referred to as failure as success, largely because the goal was actually to eliminate the primary malaria vector in Sardinia, which was Anopheles lebranchiae. But the thought was that given what SOPR had managed in Brazil, the fact that we had this new, almost magical insecticide in DDT, that we could eliminate Anopheles lebranchiae from Sardinia. So the Rockefeller Foundation initially put out about $2.7 million, and they aimed to eliminate this mosquito within 2 years. This is where we start to see that it's not always as easy as we think. The program took quite a bit longer than they thought it would. Took at least twice as long. They ran into a lot of logistical challenges. Sardinia is very mountainous, poor infrastructure, so they ended up using horses and mules to drag their equipment and supplies up into some of the more remote areas. So as I said, it took twice as long, actually cost 4 times as much. And in the end, they didn't actually manage to eliminate Anopheles lebranchiae. However, they did manage to eliminate malaria. So the idea that maybe we could focus on the mosquitoes, not necessarily get rid of them entirely, we could still have a world free of malaria. And that led directly into the global eradication campaign. So this was 5 years later. The World Health Assembly declared that WHO should take the initiative, provide technical advice, and encourage programs to eliminate malaria as a worldwide. The campaign was based almost entirely on the spraying of DDT, indoor residual spraying with DDT. It was unfortunately largely considered a failure. It started in 1955. By the late 1960s, given all the logistical challenges, increasing costs, and donor fatigue, money was slowly dried up, and by 1969, the campaign was officially ended. Despite the lofty name, the Global Eradication Campaign, there were actually only 52 countries that were involved in the campaign. And of those, only 11 succeeded in eliminating malaria. I've listed them here on the right. Most of them were in Europe and islands in the Caribbean. So not exactly malaria hotspots. And they still had serious challenges in eliminating malaria. That said, there were successes even in places where they didn't eliminate malaria. For example, India had an estimated 47 million cases at their independence. And by 1964, they were down to just 100,000. Now, after the campaign ended, cases did come back, but they have never come close to the pre-elimination efforts. And then Sri Lanka actually went down from 3 million cases to 17. And unfortunately, they had some political instability. The campaign fell apart, and it was another, 50 or 60 years before they finally eliminated malaria. I mentioned that there were a number of challenges to the program, administrative. So these are huge efforts. India, for example, had 100,000 people that they employed at the height of their campaign, and trying to manage all of these people, get them the supplies that they need, get them to the places that they need to be to spray was a major challenge. They did anticipate insecticide resistance would occur, and it did. And there were some alternatives, but they tended to be more expensive. They didn't last as long, and it ended up costing the programs more than they had originally anticipated. Another issue that they found was a number of these places had exophagic and exophilic vectors. So this program was built on the idea that mosquitoes would come into the houses, feed on the people inside, and then rest on the walls. And that's true for a lot of mosquitoes that transmit malaria, but there are places where many of the vectors actually spend most of their time outdoors, and that's where they feed and rest. And then lastly, I did kind of allude to this, just the poor infrastructure and health systems made it very challenging. So notably, Africa, despite having some of the heaviest burden of malaria, was basically excluded from the campaign. And unfortunately, at the end of the day, when the campaign collapsed, there was a loss of excitement around malaria vector control, and most of the efforts that proceeded after this were really focused more on case management. So within Africa, there actually were a couple of pilot programs. I think I read there were about 20 pilot programs that attempted to show that you could eliminate malaria. None of them actually succeeded in eliminating malaria, even in these small areas. But most of them were not very well documented. The two that were the Parasitic scheme, and this actually arose during the discussions around the global eradication campaign. When it was decided that malaria was too entrenched in Africa and the health systems were too weak, it was advocated to at least do some kind of pilot to document how far we could progress if we were to implement the tools we had to reduce malaria in Africa. So the Parasitic area is actually on the border of Tanzania and Kenya, on the kind of the east side towards the coast. They sprayed from 1956 till 1958, and you can see up here on the left. I don't know if it shows up very well. Does my cursor show? Well, anyway, so this upper left, this is the impact on the mosquitoes. And you can see a very, very rapid drop off when they started spraying. We had two major vectors here in Africa. One is Anopheles gambiae and the other is Anopheles fenestis. Actually, Anopheles fenestis completely disappeared, and it wasn't seen until about 4 years after they stopped spraying. And then there was a tremendous impact on malaria prevalence. So these were cross-sectional surveys that were done regularly. Before the campaign started, parasite prevalence rates were well over 30%. And during the spray period, they got down below 5%, but they never got down to zero. And then one of the questions that came up as there was discussions around the eradication campaign and whether or not to do it in Africa was the concern that if you go in and you really reduce malaria transmission for a period of time, but you don't completely eliminate it, as soon as you remove those controls, the malaria is going to come back, and what you may have potentially done is create a population who have lost a certain degree of immunity. So they actually continue to track the population after they stop spraying. And you can see on the right, the mosquito populations, those are the lines were coming back. And it actually took a few years before parasite prevalence rose back to the levels it was seen before they started spraying. And then on the right-hand side, it's a little bit of a complicated figure. They looked at the mortality rates by various age groups, both pre-spraying, during the spray period, and then after the spraying. And what you can see is in most of the age groups, mortality dropped, obviously when the spraying happened, but that mortality actually stayed low in most of the age groups, and it never really
went back above the pre-intervention period. So there was thought that maybe, this was evidence that we could go in and we could spray or do some kind of vector control. And even if we release those, we won't have any kind of long-term serious adverse impacts. The other site that did malaria control in Africa is the Garki project. So this was in northern Nigeria, and it was commissioned by the World Health Organization. They recommended a large study to study the epidemiology of malaria and to see what it would take to drive transmission down to very low levels. So the primary tools that they used were indoor residual spraying. They actually used Propoxer, which needed to be sprayed every 2 months. And then they had kind of these concentric areas of control. So the largest area everybody got IRS. In a smaller area, everyone got IRS, and they got mass drug administration every 10 weeks. And then there were a couple of smaller areas that got mass drug administration every 2 weeks. And turns out if you do all of that, you can have a pretty significant impact. Again, like the Paré-Taveta area, they were able to drive prevalence down. These were repeated cross-sectional surveys that they did. But interestingly, if you look at what happened with the areas that only got IRS, so they did have a couple of villages that were controls, and there was really very little impact on the prevalence of malaria in those areas that were getting sprayed twice or every 2 months. Now they attributed that to a couple of things. One was just, first of all, there was so much malaria transmission going on that it was really hard to drive it down to the point that we would see an impact on prevalence. But the other was there was concern that these malaria vectors in this area were more exophilic than they had expected. So they were actually coming into the house to feed, but they were finding that they were not staying inside and resting. And that really was about the extent of malaria vector control in sub-Saharan Africa for much of this period. So this was in the 1970s. So 70 years after we realized that malaria was transmitted by mosquitoes, very little was happening in sub-Saharan Africa. So I put this figure in here just to give perspective on what things were happening globally. It shows the distribution of malaria over time. So these pink areas were areas that had malaria eliminated, usually by the 1950s, and that's mostly in the temperate areas. The more reddish areas shows where malaria was eliminated, after the 1980s. So this much smaller area. And of course, the darkest areas along that tropical belt is where malaria is primarily today. Now, this is somewhat of a misleading figure because even though it shows it's dark all across these wide areas of tropical of this tropical belt, of the 247 million cases that were estimated in 2021 and 620,000 deaths, the vast majority of those were happening in Africa. So it became clear that if we were going to do something about malaria, we really had to do something in Africa. Well, things began to change in the 1980s, 1990s with insecticide-treated nets. And actually, the history of nets goes back, or the development of nets kind of goes back to the 1970s when pyrethroid insecticides were developed. These actually have a lot of the same properties as DDT. In fact, their target site is the same target site as DDT. They're derived ultimately from the chrysanthemum plant. The pyrethrins are a class of insecticide that are very effective against insects. Unfortunately, they don't last very long. So some chemists found that you could chemically stabilize these and develop these pyrethroids. And like I said, they're very similar to DDT in that they're cheap. They are very effective against insects, low toxicity to mammalians, and they have good residual properties. So in the 1980s, there were a couple of groups that started putting these onto onto nets to provide a chemical barrier in addition to a physical barrier. In fact, they cut the nets in some cases just to show that the insecticide by itself provided much of that protection. Based on those experimental hut studies, we quickly moved into large-scale trials. There ended up being 5 large-scale trials conducted in sub-Saharan Africa. One of them was the one that Bernard had mentioned that we did in Western Kenya. So this is just outside the town of Kisumu, along the shores of Lake Victoria. We had 2 areas, Asembo and Gem. Asembo had a population of around 55,000 people. Gem was around 125,000 people. This is an area with very high transmission. Back in the late 1980s, John Beyer and his colleagues estimated the entomological inoculation rate of over 200 infectious bites per person per year. And the transmission here is year-round. So there's 2 rainy seasons, but you can get rainfall in pretty much any month. So we see transmission throughout the year in this area. We randomized the villages to either receive nets or not, and then followed them over 2 years. And I mentioned the malaria transmission is very high here. The primary malaria parasite is Plasmodium falciparum, which is, of course, the most dangerous of the human malaria parasites. And our primary vectors are Anopheles fenestis, which is strongly anthropophilic and a very good vector. Anopheles gambiae is very similar to fenestis in that regard as well, that it's strongly anthropophilic, comes in houses, feeds on people, and is a very good vector. And then Anopheles gambiae has a sister species, Anopheles rabiensis, which is very similar morphologically, but has a lot of differences in terms of its behavior. It's still a vector out there, but they are less likely to come in houses, and they're more likely to feed on alternative hosts such as cattle or goats. So just to quickly go through some of the results of that study, we saw a massive reduction in transmission. We had about 59% fewer Anopheles gambiae, about 95% fewer Anopheles fenestis. And when you combine that with the sporozoite rates, we estimated about a 90% reduction in transmission. That led to healthier pregnancies, so reduced parasitemia among pregnant women, reduced severe malaria and placental malaria, and that resulted in a reduction in the percentage of low birth weight babies. And then amongst children, we saw a massive reduction in the incidence of malaria. We had a birth cohort where we looked at time to first infection, and that increased from 4.5 months to over 10 months. We saw a reduction in severe anemia and reduction in visits to the clinic, sick visits to the clinic. But our primary outcome was actually all-cause child mortality. Not malaria specific, this was all-cause child mortality. And overall, we saw a 26% reduction in infant mortality and a 14% reduction in child mortality from 1 to 4 years old. This was just one of several trials. Like I said, we did an area of very high transmission, but there was another trial on the coast of Kenya, one in Ghana, one in Burkina Faso, and then there was another trial that was done in the Gambia where their comparison was actually untreated nets. And this shows the forest plot from a Cochrane review that was done by Christian Lengler. And overall, he estimated that by implementing insecticide-treated nets, we could reduce all-cause child mortality by about 18%. So I like to attribute this to insecticide-treated nets. I think there were some other things going on. For example, we were seeing the main drug that was used for treatment of malaria was chloroquine, and that was resistance to that was increasing. It was essentially becoming worthless in much of Africa. And people began to realize that, we needed to do something about malaria in Africa. So in 1998, the Rollback Malaria Partnership was conceived, and the idea was to advocate for increased resources for malaria. And in 2000, there was a summit convened by Rollback Malaria. They brought in the heads of state from many African countries, and they made a pledge to provide insecticide-treated nets to 60% of those at risk by 2005. And then the two big donors that came in, though, were the Global Fund, which started in 2002, and then the US President's Malaria Initiative in 2005. And that resulted in a massive increase in the amount of funding for malaria prevention. So there are some other things that happened as well. For example, I mentioned that chloroquine the resistance was widespread in Africa. In the 2000s, many countries began switching their drug policy from chloroquine to, now it's usually a combination, artemisinin-based combination therapy. The other advancement with the insecticide-treated nets was the development of what we refer to as long-lasting insecticidal nets. When we did these trials, it was run by researchers, and we wanted to make sure that everybody had a treated net. And while there was some residual activity of these pyrethroids, they would wash off, or they would fall off, and if people washed the nets, they would lose a lot of the pyrethroids. So we made sure that we would go out at 6 to 12 month intervals to retreat these nets. But when we tried to implement that as a program, it did not work very well. People they either didn't recognize the value of the insecticide, or just for whatever reason that they didn't make efforts to get their nets retreated. Well, that was solved by a number of companies that develop what we call long-lasting insecticidal nets. These are usually pre-treated with an insecticide, and they're formulated so that they can resist washing and regular sort of wear on them. And they're designed to last ideally for 3 years. 3 years under normal use conditions, which normal use varies from place to place, and we do see some variability in how long they last. But in general, we do see very good activity over time with these long-lasting nets. And that allows us to design distribution systems. And what we mostly do in these days is we give out nets at 3-year intervals. So we do a mass campaign targeting everybody with a net, not just pregnant women and children who are the highest risk, but the entire population. And then we know that the nets are lost over time. So we do have systems to supplement those, usually provision of nets to pregnant women at their ANC visits, and then also to their children during their EPI vaccination visits. So the result is that we have seen an increase in the coverage of nets over time. These are data that I pulled from the World Malaria Report. By about 2005, we hadn't quite reached the 60%, but we have gotten there, close to there, in terms of having at least one net per household in sub-Saharan Africa. The other thing that happened during this time was there was a renewed interest in indoor residual spraying. This is mostly through the US President's Malaria Initiative. So when we started, about 2% of the population of sub-Saharan Africa was covered by an IRS program. And by 2010, it was around 12%. And all this actually led to decrease in malaria burden in sub-Saharan Africa. This is a slide that I probably overused, but I think it's really nice for a number of reasons. So this shows the decline in malaria. This is actually the red line over here. Shows the decline in malaria in terms of parasite prevalence. And these were measured in national surveys that are conducted throughout Africa, usually on a 3-year cycle. The black line right here, this is the counterfactual. So this is what we think would have happened if we hadn't done anything. And then these various shades of green, pink, and purple indicate the contribution of various interventions to to that decline in malaria. And so what we saw was, or what these authors found was that the prevalence of malaria had declined by about 50%. The incidence of clinical disease had declined by about 40%. And actually about 68% of that was due to insecticide-treated nets, with another 13% due to the implementation of indoor residual spraying. So I like to do this as a kind of a plug for us vector biologists, that it does work. We can have an impact on malaria using anti-mosquito measures. So we actually saw some similar trends in Western Kenya. These were pulled together from a variety of surveys. We actually CDC started working in Western Kenya in the early 1980s. And we really started ramping up efforts in the early 1990s. And during that time, malaria prevalence was around 80%. You can see here it's dropped down. We've gotten it down about a little bit less than half in this area that we've been working for many years. So just for reference, the insecticide-treated net trial that we did happened from 1997 to 1999. There was one of the first mass campaigns in Kenya happened in 2006, although this one only targeted children under 5. And then that's not the only thing going on. I mentioned that there were changes in drug policy. So in 2004, Kenya finally switched from chloroquine to amidiaquine. And in 2006, they finally switched over. They eventually switched over to one of the artemisinin-based combination therapies. So during this time, we've been measuring the entomological inoculation rate. This is simply an estimate of it's really basically the product of the number of mosquitoes that are feeding on man multiplied by the number that are infected. And early on, in the early 1990s, we actually saw EIRs of around 280, which is pretty high. They did decline before the BetNet trial. We're not quite sure why. Came down to about 125 in 1994 and around 50 in 1995. We did have to switch the way that we collected mosquitoes, just because of the way the bed net traps work. We replaced those with insecticide-treated bed nets, so we switched over to light traps. So take this with a grain of salt, but basically what we continue to see is about a 90% reduction in the entomological inoculation rate in this study area. And it's continued to remain low through 2009. One of the other interesting things is changes in the species composition. So I had mentioned Anopheles fenestis in the Pare tiveta scheme essentially disappeared for about 8 years. We didn't quite get it to disappear completely, but it became a very rare mosquito after we implemented bed nets. The other interesting thing was when we started looking at the relative proportions of Anopheles gambiae, which remember is a strongly anthropophilic mosquito, tends to come in houses, feed on people, rest inside, versus Anopheles arabiensis, which sometimes it'll come in, sometimes it'll rest inside, but it's perfectly happy to feed on non-human hosts and find resting sites outside. And so what you see in this is the Anopheles gambiae, proportion of Anopheles gambiae is up on the top and in black. And before the bed nets came in, that was mostly what we saw inside houses. And then I'm not exactly sure what happened. I'm guessing this may have been a result of that campaign that happened in 2006, but we saw a sudden switch. And Anopheles gambiae has also become very rare in this area. In fact, this has continued to this day. We occasionally find pockets where Anopheles gambiae is predominant, and sometimes it pops up like during the rainy season. But in Western Kenya, and this has been reported from a number of other areas in East Africa, Anopheles arabiensis has become the predominant species of this complex. That said, I kind of only showed data up until about 2010. We've continued to monitor things, and unfortunately, we stayed where we are, but unfortunately we haven't made any progress since then. And that is despite the fact that we have ACTs as our primary or their first line therapy for uncomplicated malaria. We've done a couple of additional mass campaigns with nets, and in this case, we were aiming for universal coverage, so we're covering everybody, children and adults. And yet, malaria has persisted all this time. And this is a trend that has actually been seen in all of Africa. That the paper that Samir Bhatt, which I just showed a few slides ago, showed that massive reduction from 2000 to 2015. So these are data that I pulled from the World Malaria Report just on the African region. On the left is the number of cases per year, and on the right is the number of deaths per year. The cases have stayed steady, although incidence was mostly declining because we have a population that's increasing. But you can see the deaths came down quite a bit. We were up over 800,000 deaths around 2000 due to malaria, and we got down under 600,000 deaths per year around 2015. But you can see that's leveled off, and it's even starting to increase a little bit here in more recent years. So we started thinking about what's going on here in Western Kenya. This figure shows the coverage of nets. We CDC actually provided nets in this early period here. This was the population that had participated in our bed net study, and we felt like we had to continue to provide nets. We ended that when Kenya started when the Kenya program started implementing nets on their own. But we suspect that maybe they didn't do quite so well, because you see a little bit of a drop here. But that drop actually occurs at the lowest point of prevalence in our study area. And then again, with the mass campaign, coverage came back up. And this is really about as good of bednet coverage as I think you're going to find, just because people, even if we can get them nets, they often will not use them for whatever reason. So we don't think it was an issue of we didn't have the nets out there. We are concerned about insecticide resistance, and I suspect this is probably playing a role. We didn't have really great data in Kenya just because the numbers had gone so low. So I'm presenting some data from Malawi here. This shows deltamethrin resistance on the left. So these are wild populations that were brought in, exposed to a diagnostic dose of deltamethrin. And you can see the mortality had declined pretty steeply from 2011 to just to 2015, so just 4 short years. And then on the right, we were testing the efficacy of bed nets with a susceptible strain, Anopheles gambiae Kisumu, and then wild Anopheles fenestis that we brought in from the field. And we usually expect 100% mortality in these bioassays, although some of the nets, like the Ollie set, has some repellent activity, so we often see lower mortality, even with the susceptible strain. But you can see with the resistant strain, we see very low mortality. These are nets that are basically right out of the bag. They've never been used, never been washed, and we're getting very low mortality with these mosquitoes. And again, this is a trend that we're seeing throughout much of Africa. This was a review paper that was done in 2016. So Anopheles gambiae on the left and Anopheles fenestis on the right. The blue dots are exposures to deltamethrin, and the orange are permethrin. And you can see for both species, there's a general trend for reduced mortality over time. And then the other thing to note here is that I mentioned Anopheles fenestis had largely disappeared in Western Kenya. Well, it has come back. So the figure on the left is specifically our work in Western Kenya, where you can see is fenestis made up a very small proportion of mosquitoes the species collected from about 2002 to 2008. And in 2011, it suddenly became the predominant mosquito. There was a review paper that was done on the Anopheles phonestis in East and Southern Africa, and that was a trend that we saw pretty much in all of these countries, where Anopheles phonestis has come back and is really the predominant vector in East and Southern Africa. So we do have a couple of tools that we have started implementing for dealing with these resistant mosquitoes. The first is PBO nets. So piperonyl butoxide it's not an insecticide itself, but it's a synergist that restores susceptibility by basically it inactivates metabolic enzymes associated with the detoxification of pyrethroids. So we've done a number of laboratory assays that show very clearly you can restore susceptibility. There have been some experimental hut studies and then a couple of cluster randomized trials showing that these products work better than a pyrethroid-only net. And just very quickly, I'll show a slide from Malawi where we actually rolled out insecticide, indoor residual spraying at the same time we did a mass campaign. Some of the districts got PBO nets, some of them got standard pyrethroid-only nets, and we saw about a 54% reduction in the incidence of malaria in the districts that got the PBO nets, and just a 28% reduction in those districts that got pyrethroid-only nets. And the PBO nets actually had a very similar impact as IRS. The other products that are now available for implementation are chlorphenapyr nets. So chlorphenapyr is an actual insecticide that works by disrupting the production of ATP in the mitochondria. It's kind of a hard insecticide to test because unless mosquitoes are actively respiring, it doesn't kill them. But if you put them out into the experimental huts, you can see a massive increase in the mortality of mosquitoes that enter the huts compared to a pyrethroid-only net. And like I said, there are two products now that are available for procurement and are currently being rolled out in a number of countries. The last challenge I wanted to raise was that of mosquito behavior. We know nets work, or we think nets work, because mosquitoes that transmit malaria, at least in sub-Saharan Africa, tend to come inside, feed on people late at night while they're sleeping. And this is shows a figure of Anopheles phonestis from Western Kenya. This is very typical for phonestis. They really start biting around midnight, and that continues until about 6 in the morning. This other line is the outdoor mosquitoes we capture outdoors. So we have people stationed indoors and outdoors. And you can see they much prefer to feed indoors. And then we can map that to the behavior of people. So we either do questionnaires or we directly observe where people are at various times. And we can kind of overlay their behavior with that of the mosquitoes. And what we see is that, at least with Anopheles phonestis, and this was several years ago, about 98% of the bites occurred amongst people while they were indoors, and 94% of them occurred while people were asleep. Unfortunately, we are starting to see some changes. This was a study that was done in the Central African Republic. There's a lot on this slide. So it's 4 different species. The upper figures show a 24-hour clock, and you can, if you look closely, you can see where the mosquitoes are biting at different times. But if you look at the lower figures, they show one line for each figure is the number of mosquitoes biting indoors. The other is mosquitoes biting outdoors. And it's cumulative from 6 a.m. until 6 p.m. And what you can see is indoors in all of these, there's quite a bit of biting that occurs between 6 a.m. in the morning and 6 p.m. at night. And they estimated about 20 to 30% of the bites were actually occurring during daylight hours. So that is not something that we are terribly well equipped to address right now. But the last thing I do want to point out is that as good as bed nets have been, it doesn't take a lot of mosquitoes to have a lot of malaria. So this figure on the left shows the relationship between malaria prevalence and the entomological inoculation rate. The figure on the right, they've just categorized the EIRs by 1 to 10, 11 to 100, and above 100. So we started in Western Kenya with EIRs in 1993 of around 280. We knocked it down by 90%, but that still only gets us into this category. And even if you use 1995 as our baseline, where the EIR was 50, we knocked it down by 90%. That still puts us in this category. So we may simply have gotten to the point where we've done as much as we can with insecticide-treated nets, and we need some additional tools. So one tool which is making a bit of a comeback is larval source management. WHO several years ago recommended that larval source management only be done in areas where habitats were considered few, fixed, and findable, which was intentionally vague, but really designed to sort of discourage programs from diverting resources from ITNs and IRS. But that said, there are a number of new tools out there. There's a lot of new insecticides. We have remote sensing, drones. So and given the fact that most countries have really reached about the highest level of coverage with ITNs that they can get, there's increasing interest in moving towards larval source management again. House modification is another area of interest. These two figures on the right, there was a recent series of articles in the New York Times, and they mentioned house modification as a tool for reducing malaria. Interestingly, the figure on the left goes back, that's over 100 years old. That was one of the first trials of screening houses, and that was actually done in Italy. With CDC, we've been working in Uganda to evaluate two different types of house modification. One is a full screening, where we're simply doing untreated screens, covering the windows and these air vents. This is a study that, this other intervention is eave tubes. And the idea is that if houses have completely closed the eaves, you can drill these holes in there, put a PVC tube, and then there's a mesh insert that goes in there that's treated with insecticide. And we just completed our trial just a few months ago. It was a massive trial. It was a lot of stakeholder engagement, and a lot of effort to put this intervention out there. It actually took about 4 months to implement the house screening and 2 months to do the eave tubes. But that said, we don't have the primary outcome. We haven't completed the analysis on that one. We're still doing the data cleaning. But we did do some cross-sectional surveys, and after 12 months, we saw a reduction in parasite prevalence of 24% for people living in villages with eave tubes, and 30% reduction in the villages with full screening. The other big question that we are dealing with is the cost. There's a huge upfront cost for these. In comparison, a bed net is about $3, $3 or $4. In our case, we estimated the 5-year cost for screening to be about $130, and for eave tubes about $84. So we're, obviously if these last longer, it will bring the annual cost down, but it's still a significant investment in resources. There are actually 2 trials that are basically completed. The one in Uganda a second one in Ivory Coast. There's actually going to be another third one, again, done in Ivory Coast, which just started, I think, a few months ago. That said, right now, WHO does have a kind of a weak recommendation for house modification for screening with untreated netting. And for us within PMI, we actually have followed on that. We will implement on a pilot scale house modification, although admittedly we haven't. I don't think any country has taken up that guidance just yet. So I have two more interventions that I want to talk about, and I'm going to go through them really quickly. One of which I've been working with people here at the University of Notre Dame, which is spatial repellents. So there are a number of products that are available on the market. Coils are widespread in many of these places in in sub-Saharan Africa. I think we generally think of spatial repellents as kind of creating this bubble, which mosquitoes will kind of enter into it and then turn around and go in the opposite direction. It's actually a little more complex than that. There is some movement away from the stimulus. There's also creates confusion around mosquitoes, like they will enter that space, but then some seem to lose their track and won't feed. And then some of these are actually insecticides, like DDT actually has some spatial repellent properties. Transfluthrin and metafluthrin are pyrethroids, so they do have some toxic effects as well. And this is a trial from Indonesia. This was conducted by people here at the University of Notre Dame. It was a trial that was done in 24 villages. They did see a positive effect of the spatial repellent on incidence of malaria. Unfortunately, malaria was going down in general, and it becomes harder to detect a significant difference. So while the overall results were generally positive, without that statistically significant difference, WHO said, well, we still need to see evidence from a couple of trials. So the UNITAID funded several trials, including one in Western Kenya. There's a second one that's ongoing in Mali. And then there were a couple of trials around Aedes-borne viruses, one which was done in Peru and another that's ongoing in Sri Lanka. We just completed the trial in Kenya, and our interim analysis showed a significant effect of spatial repellents on the incidence of malaria as measured by time to first infection. So we're hoping that the Mali trial has similar results, and then we will take that to WHO, the Vector Control Advisory Group, who will then hopefully recommend that to the Malaria Policy Advisory Group, and we can have this established as a new intervention class hopefully by the end of next year, if not early 2025. And I do think there's a lot of interest in this because there are a number of what we would call second-in-class products that are kind of waiting in the wings. The one on the far left is the mosquito shield. That's what we used for our trial. It has to be replaced every 4 weeks, which is quite an effort. That was donated by SC Johnson, and they now have a new product which they're looking to scale up called the Guardian, which they think will last for up to 12 months, and that could be that would really be a game changer. And then the other nice thing is that this would allow other products, other manufacturers to come in. So on the right here, there's a product that we tested in Western Kenya with metafluthrin, and again, we showed some really, really exciting results in terms of reducing mosquitoes, even outdoors where we thought that airflow might reduce the efficacy. The last tool that I wanted to talk about was attractive targeted sugar baits. This has gotten a lot of attention in the last few years. So we know mosquitoes feed on vertebrates. They take that blood to help for egg development, but they also need sugar as a source of energy. And both males and females will take sugar. which they get from a variety of sources. There have been a couple of studies where they've shown that you can manipulate the vegetation, like remove certain types of vegetation, and you can see a decrease in malaria transmission. So that gave the idea that perhaps we could manipulate this for malaria control. So one of the first studies was done in Mali, and it was a very simple study with 2 villages. They were monitoring mosquito populations every day in each village. And then after about 8 days, they went in and they sprayed all the vegetation with a slurry that they developed themselves. It was derived from guavas and honey melons, and it was spiked with boric acid. And they saw about a 90% reduction in the total numbers of mosquitoes. And then in the older mosquitoes, those that had completed 3 gonotrophic cycles, they saw an even greater impact. Now, using that as a approach is probably not the best way. So there's an effort to develop actual bait stations. And this is a product that is currently undergoing testing in a number of locations. This was right here was the preliminary entomological studies that were done in Mali, and they actually showed very similar results to that initial trial. So this was done in 7 villages. They monitored them over the rainy season, and during the peak rainy season, they saw about 57% fewer Anopheles gambiae, and they estimated a 97% reduction in these older mosquitoes that are responsible for the transmission of malaria. So there are currently 3 large-scale trials going on in Africa. The Zambia trial just finished up, and they did see a positive impact of the ATSBs. Unfortunately, it was not statistically significant. So we're still waiting to see what will happen in the trials in Kenya and Mali, which are due to complete next year, early next year. So one of the last things I wanted to talk about was a few of the threats that still remain. And one of the biological threats that we're starting to grapple with is the introduction of Anopheles stevensii to Africa. So this is a mosquito. It's native to the Indian subcontinent, but it was found in 2012 in Djibouti and has since spread to 8 countries that we know of in sub-Saharan Africa. It's not the efficient vector that an Anopheles gambiae and Anopheles fenestis are, but it does provide some unique challenges. It's able to its larvae are able to develop in artificial habitats, and that's allowed it to invade more urban environments. And because it can get into these artificial habitats, if people have water storage during dry periods, that allows the Anopheles stevensii to persist during these periods. The other challenge is it largely feeds and rests outdoors. So we have suspicion that ITNs and IRS are really not going to be very effective against this mosquito. And it is resistant to most of the insecticides that we're currently in use in sub-Saharan Africa. And there is some evidence that it is a problem. In Djibouti, the year it was found, they had 27 cases of malaria. As of 2020, they had over 70,000 cases. The entomological monitoring during this time period, they've only found they've not found any other species except Anopheles stevensii. And then you can see where it's spread throughout Ethiopia. They've used modeling that indicates they can see about a 50% increase in malaria, and that's going to cost them an additional $72 million in control costs. But so far, the only documented outbreak in Ethiopia was in the town of Diradawa, which happened a couple of years ago. And then lastly, on Anopheles stevensii, this was some modeling that was done, some habitat niche modeling that was done a few years ago. And it's estimated that there's going to be 126 million, there could be as many as 126 million people at risk of malaria in urban areas. And there's, right now we are we really don't have the full resources we need right now for malaria as it is. If it expands into urban areas, that's going to really draw resources away from where our efforts are currently focused. Then the other threat to malaria control is just the lack of investment. I actually came in early on. I started in 1997, and so I got to experience this massive growth in investment in malaria. But you can see that around 2010, things have really kind of leveled off. And actually, in the latest World Malaria Report, the total estimated need for malaria prevention and control was about 7.3 billion. So we're at less than half of that right now. So just to try and wrap up really quickly, one of the things that came out of the global eradication campaign was that we thought we could do everything with a single intervention and take care of malaria. And I think we've learned that no, we really need multiple interventions, and it's probably going to be tailored to different malaria transmission dynamics in different settings. I think there's been a massive increase in the amount of investment in research. We've been fortunate in the last few years to have these investments in ATSBs, spatial repellents, house modification. I didn't talk about it, but surveillance is, our surveillance tools are constantly getting better. They're still very weak. But for example, in Western Kenya, we had active surveys going on, and we're largely stopping that now and relying on the routine health systems for some of our evaluations. And lastly, just malaria control should be a campaign, should not be a campaign. It should be a policy. It really is a marathon, not a sprint. And so I'm a little worried that we have hit a plateau in our investment in malaria control and prevention. But I'm hoping we can see that investment increase over the years. And then just very lastly, I mentioned early on that Dr. Craig had a very important role in my life. I met him at UNDERC in 1990. Did not have any thoughts of becoming an entomologist or working on mosquito biology. And just in one of his conversations, he suggested I take his medical entomology course. And so 30 some years later, here I am. And it's impressive to see the influence he's had, not just on me, but on many other people. So this is a slide I borrowed from Ned Walker. I highlighted a number of other people who've worked on malaria. And it's a small world, but I've interacted with a lot of these people, and just want to let you know I really appreciate the influence he's had on me, and it's been a very rewarding career. I think that's it. Thank you.
Thanks, John. I'm glad Dr. Craig convinced you as an entomologist. For those who could hang around, we do have some time for questions. So I think there's a microphone back there. If anyone, I'll just.
Hi, John. Lovely presentation and good to see you. I'm curious, in the places where the dual insecticide nets or new nets have been implemented, are you starting to see any resistance?
So the PBO nets in West Africa, I think we probably were seeing resistance or that increase in mortality that you see wasn't happening. Resistance was really most intense in West Africa. Lots of different mechanisms. So PBO really only is effective for resistance that's caused by metabolic enzymes. The P450s. In West Africa, they've got P450s. They've got target site mutations, probably some cuticular thickening. and then other metabolic enzymes. So even very early on, we didn't see much of an impact. Anopheles fenestis is actually the mosquito that it works best against, because even though they're really resistant to pyrethroids, it's almost entirely due to the P450s. So yeah, like in Malawi, we saw like a 3,000-fold increase in the diagnostic dose. We added PBO and it completely eliminated that. For chlorfenapyr, there's been some reports of resistance. I mean, so all these insecticides that we have for public health are, to be honest with you, they're cast-offs from agriculture. So they've already been used. So there have been a couple of reports in West Africa. It's not really clear, and part of that may be that, you know, it's such a new insecticide, and its mode of action is different enough that actually measuring resistance is a challenge. So because it works on the mitochondrion, if mosquitoes aren't respiring, they can be exposed to pretty high doses, and it doesn't seem to affect them. So developing a tool to actually measure resistance has been a challenge. So we actually think, well, maybe we just don't have the right diagnostic dose. But it certainly is something that we're very concerned about.
Yeah, so the vector control mechanisms used in India, are they transferable to Africa?
Mm-hmm. So they have largely relied on IRS. In fact, even after the global campaign collapsed, India was able to marshal a lot of their own resources and control malaria that way. They are doing a lot with ITNs, and I think they're also doing some larval source management. I think that the challenge is that there's the transmission level in Africa is just so much higher. I showed that slide with the prevalence versus EIR, and there are places that have measured EIRs of like 1,000. So if you can reduce that by 90%, how much are you really going to have an impact on? Yes, Bernard.
Yeah, I just wonder if you could talk about non-insecticide-based vector control.
Mm-hmm.
2 years ago for the Craig lecture, Dr. Brian Foy, who's also a Notre Dame grad, was here.
Yeah.
He spoke about ivermectin.
Mm-hmm.
I know there's some trials going on that.
Yeah.
And two others I'm just curious about. At one point in time, there was a lot of research on developing a transmission blocking vaccine, which would interfere with parasite development in the mosquito. And then last but not least could you say anything about genetic modification of mosquitoes and how much promise that holds?
Yeah. All right. Well, I can talk about the drugs. So ivermectin is really an interesting idea. So they first noticed, I think maybe back in the 1980s when it was being used for the control of lymphatic filariasis and onchocerciasis. So they would go out and do these mass drug administrations, and they basically would knock out the worm for about a year. It didn't actually kill the adults, but they started noticing that in the few weeks after doing these mass drug administrations, that you would see a massive reduction in mosquito numbers. And actually, one of my colleagues, Ned Walker, said he was feeding his mosquitoes with blood that he commercially sourced, and one day all his mosquitoes started dying. And he actually looked into it, and it turns out that the horse, I think it was his horse blood, but they'd been treated with ivermectin. So Brian Foy has done a lot of work around this. They actually did a trial in Burkina Faso where they were, I think it was every 3 weeks, going out and doing MDA with ivermectin, and they saw about a 16% reduction in clinical malaria. I think the challenge is now they're trying to line that up with something like seasonal malaria chemoprophylaxis, which is actually done every month. And And so there's current work going on around that. But I think one of the challenges is it's a pretty short duration of efficacy. I mean, we did a small study in Kenya where we actually gave people very high dose ivermectin, and we could get an impact out to about 21 days with the high dose. But it's, you know, if you're going to have to do that every month, it's a big challenge. I just attended a little side meeting at ASTMH, and there are groups that are working on trying to have more extended life formulations, which I think is probably going to be necessary. Let's see. Then you asked me about transmission blocking vaccines. I don't know very much about it. I have to admit, I don't know very much about transmission blocking vaccines. I just know that Bill Collins, who was worked on monkey malaria at CDC, and he did a lot of tests of various drugs and various vaccines. And in fact, he liked to tell people that his lab was where vaccines came to die. But he was pretty positive about the idea of a transmission blocking vaccine. He felt like that you could get, you know, the best efficacy out of one of these transmission blocking vaccines compared to a sporozoid or or targeting other stage. The challenge with that is, you can't really give a vaccine to somebody that is not going to directly benefit them. I did have a conversation with a couple of people at ASTMH, and apparently they're looking into doing transmission blocking vaccines that they would then combine with like the RTSS or R21, which are directly beneficial to people. But that's probably got a long way to go. And then the genetically modified mosquitoes. I've long been a skeptic, but that said, there's the Oxitec group. So this is a group that developed an Aedes aegypti that has a lethal dominant allele, which they're able to turn off in their laboratory. But once you release it in the field, then the gene becomes active. So they'll mate with the local population, and the offspring will all die. I think it's all die. They may have designed it so that the males will continue on, so you can continue to have a few generations of effectiveness. And they're actually they've actually developed an Anopheles stevensii that has that same construct. And then there's a group that's working at CDC, mostly with people. I think it's Oxford. It's the target malaria group, and they have a gene construct that works very similar. You release the mosquitoes, they'll mate with the wild population, and then it's just the females that are non-viable. It targets the sex determination gene in the females, so they come out as they call it double sex, but they're non-viable. But the males then can continue on and transmit that on to the next generation. And they've done some small scale trials where like cage experiments, and they showed that I think it was like 11 generations they could eliminate the entire population. My understanding is they're now doing in larger field trials or larger cage trials, but it's probably they keep saying it's like 5 years out.
Okay, well, again, thanks, John, and thanks to George Craig. Thanks